Mrs. John talking you through the Level 3 2021 Mechanics exam, NCEA. So, question 1, the fishing toy. A simple balancing toy can be made by joining two masses with a rigid wire. And here's an example of the balancing angler. This can be approximated to two masses joined by a wire, and the distance between the centers of mass of the angler and the fish is 14 centimeters. The pivot point is at the bottom of the pole under the angler, and this is 5 centimeters below the center of mass of the angler. Now, what do we have to do? Assuming that the wire has no mass, show that the center of mass X of the system is 3.75 centimeters below the pivot point. So we've got to show that as 3.75 centimeters. So taking all distances from the center of mass, you have the 30 times X equals 50 times 14 minus X. And then you get the value for X, and then the distance from the pivot point, you subtract the 5 centimeters. So that whole distance is 8.75. So this much is the whole thing minus 5. That was an achieved question. The next one, when the toy is rotated above the pivot, a torque due to gravity acts on the toy. Show that when the toy is rotated by 42 degrees, the torque about the pivot point is 0.0197. So the important thing is torque is force times the radial distance, the perpendicular radial distance. So the force is the total mass times g, so that gives you the force, and it's 0.0375 sine 42 of that, because it's at a 42 degree angle, and then you get the answer. Okay. Moving on to the next one. The rotational inertia for the whole toy is the sum of the rotational inertia of each mass. The rotational inertia of each mass is given by I equals mr squared, where m is the mass and r is the distance from the pivot. So what do we have to do? Use the information given to estimate the rotational inertia of the toy above the pivot point, and hence its angular acceleration when released from the position shown. So there are two things to do. So that's a merit question. So rotational inertia is m times r squared for one, m times r squared for the other. How did I get that number? So this is the m, this is the mass, that's 1r squared, this is the other mass, and the other r squared is just that distance, so it's 14 minus 5, and that's how you get the 9, but I have to convert that to meters. And then so you get the total rotational inertia, and then you get torque is I alpha, and you get your angular acceleration. Moving on, when the toy is released, it goes back and forth and eventually comes to rest. So two things to do. Discuss the energy transfers and explain why it always stops in that exact position. So while the toy is going back and forth, the energy changes from kinetic to gravitational potential energy. So if you said that much, it's an achieved. Now, but why does it come to stop? The reason why it comes to stop is while it's oscillating, some of the energy is lost in the form of heat due to friction, and since amplitude is an indication of energy, the amplitude will decrease. It will finally stop in the rest position, and the reason why it stops there, it's in that position there are no unbalanced forces. So the force downwards equals the force upwards, and there's no other force. Or there will, so because there is no net force, there will be no net torque, which will cause it to accelerate. So you wanted all what I've highlighted in pink in your answer for your excellence. Satellite in an unusual orbit. So here you've given the mass of the Earth and the Sun, and in the Deep Space Climate Observatory satellite is in a very unusual orbit of the Sun at the L1 point. So what it does, it kind of goes around the Sun, but at the same time it kind of goes with the Earth as well. Okay, so the satellite is 14.81 times 10 to the power of 10 meters from the Sun, and it's this distance from the Earth. So both these distances are given. A magazine article states that the L1 point is where the gravitational forces of the Sun and the Earth are balanced. Explain why this cannot be true if the satellite is moving in a stable circular orbit. Now, the important thing is for circular motion, which is accelerated motion, is that means there has to be an unbalanced force. So this unbalanced force is your centripetal force, and what does it do? It changes the direction of motion. If that unbalanced force was not there, then the satellite would move in a straight line. So you could state either this point or this point to get you achieved. Now, the satellite, due to its L1 position between the Earth and the Sun, is under the influence of the gravitational field of the Sun as well as the gravitational field of the Earth. Now, show that the net, the moment you see net, it means it's the difference between these two gravitational field. Okay, so that the net gravitational field strength G at position L1 on the satellite, if it's moving in a circular orbit, it is this value, and it's also consistent with it having a period of an Earth year of that many seconds. So what do I do? The net gravitational field strength, so this has to be the net gravitational field strength, is the difference between the two gravitational field strengths. So this is G, this is your Sun, and I put the little m as for the Earth's mass, the radius from the Sun, and the distance from the Earth. Because G is a common factor, I've just taken it out and I've solved it. So if you've done so much, you get an A. Okay, and if you got the answer, that's your M. And then you also have to say, now V is 2 pi at the L1 point. V is 2 pi r over T. It's going around the Sun, so you've got to take the radius of the Sun. And T is the period of the Earth around the Sun. So when you substitute those values, you get the value for V. Now, for circular motion, you know V squared is Rg. So you get G is V squared over R, and that's how you get this, which is very similar in value to that. So there's your excellence. Now, the satellite has special cameras pointing at the Sun and at the Earth. So it has to spin with a period of 1 Earth year to keep in line with these objects as it orbits the Sun. The solar panels on the satellite could be moved closer or further away from the satellite to adjust the spin speed. Explain how moving the solar panels further from the satellite would affect its angular velocity. So you don't have to talk about it coming towards it, but this is away from it. So moving the solar panels further away would mean the mass distribution has changed, as the mass is now further away from the axis of rotation. This means the rotational inertia will increase. Now, the angular momentum remains the same because there's no external torques, so that remains the same. If rotational inertia increases, your angular velocity is going to decrease. So that was merit. Now then, the picture has been removed, but I kind of just sketched a little picture for you to get an idea. So a small fragment of an icy comet hits the spacecraft and sticks to one of its solar panels at a distance of 1.42 meters from the axis of rotation. The fragment has a mass, so there's your fragment, of 0.780 kilograms, and it increases the angular velocity of the satellite by this amount, and the total rotational inertia is 179 kilogram meters squared. So what do we have to find out? The impact speed of the fragment relative to the satellite. Okay, so we don't know the mass of the satellite, we don't know what's the angular momentum of the satellite, but we know what the change is. Okay, so the change in angular momentum is determined by the total rotational inertia and the change in angular velocity. So when I multiply both those, I get the change in angular momentum. So this change in angular momentum would be the angular momentum of the fragment. Now, because it's coming straight at it, we've got to use the other formula, L is equal to mvr, and get the value for V. And that was a merit question. Moving on, question 3, car suspension. A simple car suspension system rests the weight of the car onto 4 springs, each attached to a wheel. The car has a mass of 893 kilograms. John sits on the roof in the middle of the car, then slides off carefully to quickly release his weight from the car without pushing down on it. He watches the car oscillate up and down, and it completes one oscillation in 1.14 seconds. So that is the period. That's your mass of the car. Show that the spring constant is so much. So you just go t is equal to 2 pi square root m over k. We've got to find k, but because it's square rooted, what I did was I squared both sides. So I got rid of the square root sign, and you get your value for k. But what I did was I used the unrounded value for my subsequent calculations, so it might differ slightly from the answer that's probably given on the printed sheet. Now, John wonders whether the car body is moving with simple harmonic motion. There are two conditions. One, acceleration is proportional to displacement. The other one is it acts in a direction opposite to displacement. So those are the two statements you need to make to get your achieved. Okay, John has a mass of 103 kilograms, and while he sits on the roof, his weight is supported by each of the four wheels equally. So what is the initial amplitude of oscillations, and then find the maximum acceleration. So in this one, you use F is equal to negative ky. The negative is just for direction, so I just didn't use the negative sign for my calculations. So y is equal to F, so don't forget to multiply by 9.81 to find the gravity or the weight force, divided by k, and you get that. So that's my amplitude, and then I get omega is 2 pi over t, so there's my omega, and I know acceleration is omega squared y, and that's how I get my acceleration. Okay, John and his friend Rick ride in the car together. Speed bumps in the road are 10.5 meters apart, and when they're traveling at 8.33 meters per second, the car builds up large vertical oscillations. So this is an example of resonance, and I explain why this happens. So large amplitude oscillations are a result of resonance, but you got to say why and when this happens. When the car's natural frequency matches the frequency with which it goes over the speed bumps. So if you said that, that's you achieved. If you forgot to say this and did everything else, you would get a merit. Okay, then I had to find the period. So v is d over t, so t is distance divided by speed, and then I get t is 2 pi square root of m over k, or t squared is 4 pi squared m over k, or your mass is you substitute everything and you get this. This is the total mass of the car, Rick and John, all of them. So to find Rick's mass, so this is the total mass minus mass of car minus John's mass, and you get that. So that's the whole paper worked out for you.